I do have a question. So like I've been using the study prep, and do you think that's a good like route
I
to
had
be
a student
successful?
last semester that used that. You're talking about the AI study prep stuff that comes with the book publisher. Is that what you're regarding
Yeah.
talking about? Yeah, he swore by it and he made really great grades. So I'm thinking it's pretty good. I had another student though that was trying to use some AI stuff and her grades went to crap. So
No.
I guess it's all a matter of one, are you using the best stuff, and two, are you leaning on it too much? You really got to make sure you solve a certain number of problems, and every problem, at least try to solve it first before you see someone else solve it for you. Uh, just because it's so easy to rob yourself of the opportunity of learning how to discover, oh, this is how I use this equation, or oh, this sign and this sign have to be opposite because they're fighting each other and that sort of thing. That's the part of physics that you just get from solving physics problems and doing a ton of them basically. So yeah, let me know. I'd say the best thing is once you've seen the lectures and attempted to read the textbook, the homeworks, the tutorial ones especially, are really good for further teaching you. At that point, you're just doing homework just to get some experience, and then the practice test gives you that experience because there's so many questions in there that you can do and get feedback on. So hopefully that works out.
Cool. Thank you. I'll let you know for sure too.
Yeah, no problem, Mike. Hey Nathan, getting ready up. I guess should go ahead and get started. All right, so I'm going to go ahead and get started, everyone. We are starting chapter four. Last time we finished up chapter three with a little bit of relative velocity formulas. Remember, we found that neat little formula: velocity of A as seen by C is equal to the velocity of A as seen by B plus the velocity of B as seen by C, with that specific order such that the inner subscripts match each other on the addition side, and the outer subscripts on the addition side match the two subscripts on the other side of the equation. In other words, AC, the velocity of A as seen by C, is indicated by A being the first subscript on the first term in the addition, and C being the last subscript on the last term in the addition. So that worked, and then I showed you that you could add a denominator to it to make it relativistically correct. And because that denominator had c squared in it, uh, that denominator means nothing unless you're going an appreciable fraction of the speed of light, say within 1%, at least 1% or higher. So now we're going into chapter four, which is called Dynamics, Newton's Laws of Motion. And they have a wonderful picture of one of our space shuttles taking off, how they had with the huge rocket boosters and all that stuff on it. And that's a classic example. But in fact, we're now going out of what we called kinematics, which was a sub branch of mechanics, into another sub branch of mechanics. This sub branch is actually called dynamics, and it's the area of the science where we learn what makes something accelerate. How do you do that? How do you get something to get a certain acceleration? And more specifically, not just a number acceleration, but if you wanted a particular formulaic acceleration, how would you go about doing that? It turns out all that was worked out largely by many, many scientists, but no one really put the big picture together until Newton in 1687 when he wrote his Principia. And in that, he really relied a lot on others. So if you've heard the quote, "If I have seen further than others, it's only because I stood on the shoulders of giants." That's a real humble statement from Isaac Newton. And if you know anything about Isaac Newton, he was sort of the antithesis of humble. He was a quite cocky dude and had a lot of enemies. In fact, in one day in his personal notebook, he said, "Forgive me, Lord, for today I wish the death of 50 people." So but he was very pious. He asked for forgiveness literally on a daily basis of God and stuff like that. He looked in the Bible for numbers and things that would tell him to find the elixir of life, to how to live forever, stuff like that. But he also was a bit of an odd card. The other part of that quote was he said that at the Royal Society, and at the time he was not the head of the Royal Society. In fact, the head of the Royal Society at that time was a guy by the name of Robert Hooke, who was one of those mortal enemies of Isaac Newton. And Robert Hooke had a bit of what we'd call the short man complex. He probably was around 4'8" to 4'10" or something, really, really short fella. And basically, what Newton's saying is, if I've seen further than others, it's not because I stood on the shoulders of hobbits like you, but of men. So he's really was being kind of cocky to Robert Hooke there as well. So hopefully that gives you a little bit more context. But the main thing Newton was able to come up with was something that was exactly equivalent to Galileo's law of inertia. Galileo had discovered in the 1600s a law of inertia. Basically, Galileo had gotten in trouble with the Inquisition. Specifically, he was teaching that the planets orbit the sun, and that wasn't really the problem. If you read, you can go to the Vatican website and you can read the actual details of what went down, and they still have it in writing. They've even been kind enough to translate it to English so that we could read it ourselves. And what you'll find is that basically, luckily, Galileo was a personal friend of a Cardinal Barberino. Really, I think it was Barberino or Barberino or something like that. It just makes me a Vinnie Barberino from 1970s television. But anyways, that was the cardinal, and that was I mean, that was Galileo's personal friend. And in the intervening period between him asking this cardinal Baronius or whatever his name was, what do I have the permission to write this book that I'm writing? And the guy said, yeah, it's fine. It sounds like you're, putting this on as an alternative way of calculating the positions of the planets and stuff of that sort. So I have no problem with that. So he got all that signed off on. In the intervening period, that cardinal became the Pope, and that Pope was okay with the book for a long time until people started reading it and coming back to him and saying that, well, they put the position of the church in in the mouth of a character named Simplicio, which basically means a dummy or a simpleton. So he got in a little bit of trouble for that. What the Inquisition basically said was that he more or less disobeyed specific orders, and he was ordered instead of being burned at the stake like Giordano Bruno or Joan of Arc were, and he was very aware of the case of Giordano Bruno, by the way. Instead of that, he was threatened a little bit until he finally recanted and said, you've probably heard it, said, yet it does not, the sun does not move. Or the earth does not move, excuse me. And then under his breath, he supposedly said, yet it does, or something along those lines. We don't have any record of him actually saying that part, but we do know that he was sentenced to in-house arrest instead of the burning to death at the stake. And he was ordered to no longer discuss or teach anything about the heavens, about astronomy and stuff like that. So he was going blind anyways. He didn't invent the telescope. He did make a better version of a telescope, and he was one of the first people, if not the first people, to turn it on the heavens. And in that, he made some major discoveries, and that's sort of what got him into trouble to begin with the church. But ultimately, when he was put in in-house arrest, he knew the thing they had to do, since he couldn't any longer talk about how the planets moved, was he needed to understand motion, because one of the things he had seen was that in no model of the universe that anybody had, not the Aristotelian model, not the not Tycho Brahe's model, not Kepler's model, and no one's model was Jupiter sitting still. And yet he discovered that Jupiter had satellites. It had objects that were orbiting around it, and he basically saw them day in and day out by looking through his telescope at Jupiter. And he saw, like, one day there was four seeming stars around it, and then the next day it was still four, but they were in different locations. And the next day it was sometimes you'd only see two of them or three of them or one of them or something like that. But if you watched it long enough, it would always appear to be four eventually around it. And he realized they were actually keeping up with it, because one of the major ideas blocking him was the Aristotelian thought that if a bird is sitting on a limb of a tree and sees a worm down on the ground in which he would like to eat, if the earth is actually moving at hundreds of miles per hour around the sun, then if the bird lifted itself up off the limb to fly down, then the planet earth would leave him behind. So that was an ongoing idea that they had in their head about how motion worked. And if that was the case, then obviously the Earth couldn't be moving around the sun. But in his case, he had found that Jupiter had these four, what he called the Medicean moons, but we now call the Galilean moons, Io, Europa, Ganymede, and Callisto. And he found that those things didn't move. Therefore, he was convinced that we just didn't understand motion. So he went into in-house arrest, tried to study motion, tried to study falling bodies. He quickly realized that the when you drop an object, its speed and the time at which it took to be dropped and then hit the ground was such a small amount of time. He had no hope of figuring out whether this object just takes off at some fixed speed according to its mass, like Aristotle taught, or if it maybe started off at zero and then sped up, sped up, sped up, reaching some max speed, or what. He just couldn't do that. But what he realized was that he could use trigonometry, allow things to roll down inclines, very gradual inclines, and then he could relate the rolling down the incline, which was a acceleration in a very specific direction. He could relate that to the vertical acceleration that gravity would cause, more specifically down, not up. And therefore, he used the trigonometry of triangles to make sense of what the actual acceleration was. And in doing so, he discovered all sorts of things about motion. So, for instance, he was the first one to give us an idea of velocity. So, an object in constant velocity or an object with constant speed is an object that goes the same distance in a given unit of time. So, if you took that time to be, a single second, then 20 meter per second object moving at 20 meters per second would travel a distance of 20 meters every single second. And if you decided to look at a smaller unit of time, maybe a tenth of a second, then it would only go 2 meters. Or if you wanted to look at a hundredth of a second, then it would only go 0.2 meters. But it would consistently go zero point 0.2 meters every hundredth of a second. That was what we called constant motion or constant velocity motion. And he was further able to figure out that basically the distance traveled went like the square of the time, which was a really big deal. So if you doubled the time of something that was accelerating, you didn't increase the distance traveled from zero to that end of time. You didn't increase that by a factor of two. You in fact increased it by a factor of two squared or four. And if you tripled the time, you increase that by a factor of not three, but by three squared, which is nine, so on and so forth. So he discovered that kind of motion. And then ultimately, he also discovered that objects fall at the same rate. And there's, some theory, for instance, some hypothesis that he probably climbed up to the top of the Leaning Tower of Pisa and dropped two objects. At this time, Italy had a pretty good bureaucracy, and we haven't found any of the necessary quote unquote forms that would have been filled out to get such a thing done. So we think that was apocryphal, but even if it wasn't, he wasn't really in a good experimental space for him to actually show definitively whether two objects really did fall at the same rate from that height. So it would not have gotten such a great result anyways. But anyways, that's some of the stuff that Galileo did. And what Galileo found was in studying those inclines, he discovered that when you let an object roll down an incline, it sped up. When you let an object roll up an incline, it slowed down. And therefore, he reached a conclusion that if an object was rolling along a perfectly horizontal surface, it should neither slow down nor speed up. It should go the same speed forever. And he went a little further than that. He allowed an object to sort of like ride a half pipe, if you will. So it would go down one side of the half pipe and then it would go up the other side of the half pipe. Now, I'm not saying he actually put a curve in it. He probably just had an incline and another incline like that, but with no curves like a half pipe. But what he discovered was when he dropped an object from a certain height on an incline, it would go down that incline and then start to go up the other incline and almost get to the same height that he had started it at. And when he was looking at it, he noticed, for instance, the motion would sometimes stop and curve a little bit. He realized that there were some small forces acting on it, so he'd go back and polish the surfaces really well. And when he did that, he found out that they got even closer to getting back to the same height as they started off. And after a long period of time, he finally reached the conclusion that, in fact, he was right. When an object is traveling on its own, its tendency is to maintain its motion in exactly that state. So if it's moving at a constant velocity due north, say, at 2 meters per second, then it's always going to try to stay traveling at 2 meters per second due north. The only thing that would make it not do that is the imposition of a force on it. So he came up with what's now known as Newton's first law of motion, but at that time would have been, well, shortly thereafter it would have been called Galileo's law of inertia. And he basically said it's as if an object has some inertia, some reluctance to change, and that doesn't answer the question. That just gives a word to make you feel a little bit better about smacking Aristotle in the face for being wrong. So it really wasn't an extra answer. He just said objects in motion tend to stay in that state of motion unless acted upon by a net external force. That was pretty much it. And that later became Newton's first law of motion. I also was in a exhibit in Salt Lake City, Utah, where where Da Vinci's notebooks were traveling around the globe, and we got to see bits and pieces of it at this particular museum in Salt Lake City. And I read one little passage in it, and it was just lucky that I happened to see this one little passage where Da Vinci basically says, well, it's obvious that if an eagle pushes down the air with a force of 50 pounds, then the air will push back on the eagle with a force of 50 pounds in the opposite direction. That is definitely what we call Newton's third law of motion, and there's Leonardo da Vinci already knowing it. What Newton did do, though, is he codified these three laws. He introduced the third law, which no one had come up with, this Newton's second law of motion. I said the third law, meaning the third one, not not the third law. But the second law is the one that Newton really created himself, and we'll learn that as well. But he went on further and basically codified the whole principles of how we go about solving physics problems in his Principia. He also, by the way, went ahead and decided to, I don't know, discover slash invent calculus. So that was kind of cool. All right. With that being said, I want to tell you the subsections within this chapter are 4.1, force; 4.2, Newton's first law of motion; 4.3, mass; 4.4 is Newton's second law of motion; 4.5 is Newton's third law of motion; 4.6 is weight, the force of gravity, and the normal force. 4.7 is solving problems with Newton's laws, free body diagrams, and then 4.8 is problem solving, a general approach. So these are the subsections that we'll be covering. As always, you should answer the chapter opening questions as well. I'm going to go ahead and go over the laws of Newton, and I want to remind you that these laws, Newton's first law, Newton's second law, Newton's third law, later we'll learn Newton's law of gravity as well. Those are not only laws that I expect you, because they're called laws and because the whole subsection is named after them, you should commit them to memory, and that includes the name of them. So it's not good enough just to know an object in motion tends to stay in that state of motion unless acted upon by a net external force. It's not good enough to know that's one of Newton's laws. You have to know that that is one of Newton's laws, and it's specifically Newton's first law. So let me go through those laws now. As I said, an object in motion tends to stay in that state of motion unless acted upon by a net external force. That's a version. It's not the version you necessarily have to memorize. I don't care what version you memorize. In fact, what often happens when I ask a question like this on a test or something like that is sometimes I'll put, maybe 20 different sentences labeled A, B, C, D, E, F, G, and each one of them will be a robust sentence, and some of them will be actual physics principles, and some of them will be complete BS. And then I'll have a list over here on the left-hand side, and one will be Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, Kirchhoff's loop rule, Kirchhoff's junction rule, Kirchhoff's rule for hot dense matter, Kirchhoff's rule for electromagnetic radiation going from hot dense matter through a cold low density cloud. All these different things will be on there, and you'll have to match them. So it's not even that you're necessarily memorizing the words verbatim, but you should be able to recognize them verbatim if I give them to you. So keep that in mind. The way your book has chosen to tell you Newton's first law of motion, it says every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. So that's the way Newton wrote his first law of motion. Every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. So that is Newton's first law of motion. Newton's second law of motion is that basically an object, if subjected to a net external non-zero force, will experience an acceleration. That acceleration is parallel to that net external force and is directly proportional to that net external force and inversely proportional to the object's mass. Again, that's my wording. You could write that as simply as a vector, a with a vector symbol over top of it, is equal to a fraction, and then the numerator of the fraction is the summation. So we use that Greek capital sigma, and then a boldface F with a vector symbol over top of it, and that's the numerator. And that sigma means sum up all the forces acting on it because it's sigma means sum, and the F are forces. So you're telling us to add up all the forces acting on the object, and then the denominator is M, the mass. So A vector is equal to the sum of the forces as a vector divided by the mass of the object experiencing those forces. So that's Newton's second law. Newton's third law can be written as for every action, there's an equal but opposite reaction. It's one of the laws of physics that a lot of people already know, even though they don't necessarily know it's Newton's third law or they might not necessarily understand what it means. But that's what it means. Another way of writing that is F12 with a vector symbol over it. That's F with a subscript 1 followed by a subscript 2. F12 is equal to the negative of F vector with a subscript 2, 1. That means the force on object 1 as a result of object 2 is equal to the negative of the force on object 2 as a result of object 1. Just by changing the order of those subscripts, I've changed what I'm saying. So when I say F vector subscript 1, 2, that means the force on object 1 as a result of object 2. And when I say F vector 2, 1, that's the force on object 2 as a result of object 1. Okay. So when I, for instance, kick a soccer ball, I am applying a force F S B, meaning the force on the soccer ball due to B, Billy, right? And then the ball feels FSB, or excuse me, FBS, which is the force. No, I said it right the first time. FSB, the force on the soccer ball as a result of Billy. So you can look at it that way. The force that I apply to the soccer ball is going to be exactly the same as the force that the soccer ball applies to me. So B S is the force on Billy as a result of the soccer ball. If I kick a soccer ball, let's say due east, and I kick it completely horizontally with a force of 100 newtons, okay, then I'm kicking this ball east horizontal with a force of 100 newtons, then I don't get that for free. In fact, the ball is going to hit my leg with a force of 100 newtons due west and perfectly horizontal. So that's what Newton's third law says. Another version I've heard in science for or physics for art majors is you can't touch without being touched. That's sort of another thing. You'll learn that's also the reason that it's so hard if you've ever tried to kill a fly in the air just by, smacking it. You normally can't do it. You're going to hit the fly and he's going to, fly off a little bit. He might be stunned for a second and fly a little weird, but he's probably not going to die. And maybe that's not what you want to do anyways. But the main thing is, why is that the case? I've killed flies numerous times, but you can't do it that way. Well, if you think about it from a Newton's third law case, you're trying to take the huge force that you could, in principle, put on someone, especially if you've been watching these ESPN slap fight contests that they have. Obviously, slapping someone can do a great deal of damage. So you wonder, why can't I do that great deal of damage to the fly? Well, remember, whatever force you have to, or you're going to try to apply to that fly has to be able to apply to you. And if you can't, you just can't. And that's the case. If you apply Newton's second law and say, hey, I'm going to put this huge force on this fly, well, what you're going to discover is this huge force on this fly a very small fraction of it's going to be required to accelerate that fly up to the speed of your hand when you come flying across and then hit him. And once it reaches that speed, you're not going to be able to impart any more force on him, because the only way you were able to impart a force in the first case was to make his velocity go from not matching your hand to matching your hand. So, deeper thought requires you to understand that, oh, okay, because the mass of the fly is so small and the acceleration is proportional to the total force and inversely proportional to the mass, that means the acceleration with that itty bitty mass is going to be very large for a given force, and it doesn't have to be a large force. Because of that, maybe and I go to hit a fly, it's just sitting here perfectly still. Even if I'm an upper level athlete and I can throw a baseball at 105 miles per hour, then 105 is about as fast as my hand can move. Well, how much force does it take a itty bitty fruit fly, for instance, to be accelerated from 0 meters per second up to 105 miles per hour? It's going to take a very small amount of force. That small amount of force, of course, uh, is really small, and because of that little smallness of the force, that means that's the maximum that you can do to that fly, and that small force is not very much. It's not going to kill him. It might knock him silly for a little bit, but that's about it. Same thing if you try to hit a piece of toilet paper or tissue paper in the air. Try to do that really hard. You can't do that either, because it takes such a small force to accelerate that tissue paper up to the speed of your hand. All right. Now that we've got all that, I think it's best that we go ahead and jump into some examples. So we're going to jump into conceptual example 4.1. So I am going mostly by the book here using those examples. If you have your book out, that would be a very helpful thing. If you don't, I'm going to read the question as thoroughly as I can. So hopefully that's good enough. But just be advised, if I'm going too fast, you definitely want to have the ebook open and flip back and forth between it. Okay, so let me go ahead and share my screen with you folks. So conceptual example 4.1. This one probably won't require much writing, so I'm probably not even going to write it down. But conceptual example 4.1 says Newton's first law. A school bus comes to a sudden stop and all the backpacks on the floor start to slide forward. What force causes them to do that? By all means, if you have any questions like that or have an answer for that, by all means, just blurt it out. It's fine, or you can chat it in by typing it into the chat. I've got my mixed words up there, but anyways, I think y'all understood what I was saying. So you can do that. The big deal is here that that's not. It's sort of a trick question, if you will. In fact, it seems natural to answer this question because we all actually have this Aristotelian idea of physics, which is kind of weird because we never went to, any of the ancient Greek schools or anything like that. Yet we still have this inclination that that's what the laws of physics are. And that's the exact same thing that caught Aristotle. It looked like what he said was right. And one of the things he said was that objects tend to come to a stop. And actually, what he really said was objects, well, go back a little further. He said there were 4/5 elements: earth, wind, fire, and water. And each of those elements had their natural place. And whenever an object was moving, trying to get to its natural place, that was natural motion. When you tried to make it move some other way, that was called violent motion. Natural motion was self sustaining. So, for instance, something made of earth is trying to get to its place, and its place in the universe is the center of the earth. So if an object made of earth is falling towards the center of the earth, then that's its natural motion and requires no force whatsoever. It's just going to do it. And in fact, it's going to do it at a rate proportional to its mass. So if one object is 100 pounds and the other object is 200 pounds, the 200-pound one's going to do it twice as fast as the 100-pound one. That was the laws of physics according to Aristotle, and that was the way he thought of things. We now know that that's not the case. In fact, Galileo's law of inertia and therefore Newton's first law of motion is really the truth. Objects in motion tend to stay in that state of motion, which means objects maintain a constant velocity. That's the shortest way of saying it. An object maintains a constant velocity unless a net external force is acting upon it. So when it says a school bus comes to a sudden stop and all the backpacks on the floor start to slide forward, what causes them to do that? It's really their inertia. It's not a force that's doing that. In some senses, a lack of a force. If there was enough friction force between the floor and the backpacks, then they'd stay where they were. But since there's not enough friction force, the school bus, which might be going 35 miles per hour, and therefore all of the book bags and all of the students in the school bus are going 35 miles per hour, if then all of a sudden the school bus slams on brakes, it goes from 35 miles per hour to zero. And if there's enough friction, then all the things on the floor will go from 35 miles per hour to zero. But if there's not enough friction, then those things are going to try to continue moving on at 35 miles per hour. Now, there might be some friction, in which case they're slowing down. So luckily, the book bags aren't flying up to the front of the bus at 35 miles per hour, but maybe they're still flying at 18 miles per hour, which is still pretty bad. Okay. So that's the answer to this. There is no force. What force causes them to do that is actually not a force. It's the object's inertia, and we measure inertia because it turns out to be the same thing as our mass, and inertia in the SI system is measured in kilograms. In the CGS system, it's measured in grams, and in the British system, which is the one we use, us in Myanmar, and that's it really. Uh, in that system, the unit of mass is technically the slug. We don't use that, obviously. In fact, we just completely jump over that. So if you go to Great Britain and someone says, "What do you weigh?" and they tell you, you tell them an answer in kilograms, that's what they're expecting. In America, if someone says, "What do you weigh?" they're expecting an answer in pounds, and the pound is a unit of force or weight, not a unit of mass. So they're just skipping it by using an entirely different quantity. In some sense, a more relevant quantity because it's really how much gravity is attracted to you as a result of the gravity of the Earth, whereas a mass is a property of your of you and what you're made of and that sort of thing. So, any questions on that? Your book does talk a bit about inertial reference frames. I want to point that out specifically because when we go to use our coordinate systems and set up our free body diagrams, we want to make sure we're in inertial reference frames. And since I told you that Newton's first law of motion is equivalent to Galileo's law of inertia, this might come into play here. Specifically, if you see Galileo's law of inertia or Newton's first law of motion being violated, then whatever frame you're seeing that in, that frame is not an inertial reference frame. For instance, if you attached a video camera to one of those merry-go-rounds that you see in a public park, the thing where you can run beside it and get it going faster and faster and faster and then jump on the round platform and spin around really fast. Okay, if you mounted a video camera to that platform where you could only see the platform and not the outside, you'd have no way of knowing whether that platform is rotating. Well, if you took a basketball, say, and stuck it in the dead center of that disc that you're rotating, what you would see is, unless the thing was sitting perfectly still at exactly the right spot, you would see that basketball sitting perfectly still, and then all of a sudden it would take off and shoot radially outward, or at least it would appear to shoot radially outward. And that is a violation of Newton's first law of motion because you don't see any force causing that to happen. You just saw it blindly go from a velocity of 0 meters. And I shouldn't say blindly, I should say uh, unreasonably with no force acting on it, go from 0 miles per hour sitting perfectly still to moving with some speed with no apparent force acting on it. So that is a non-inertial reference frame. The Earth rotating, depending on how many decimal places you want to do a particular measurement in, can be considered an inertial reference frame or a non-inertial reference frame. It all depends on what you're measuring and how precisely you're measuring it. But more specifically, Galileo, or excuse me, I should say, Einstein later used the idea of inertia to separate out gravity because his idea was that gravity wasn't a force. It was basically a misunderstanding of inertia. And what ultimately he decided was that space was curved, and it was that curvature of the four-dimensional space that caused things to move towards each other if they had mass. And the way he took that out when he when he gave us our special theory of relativity, he said the laws of physics are the same in all inertial for all inertial observers. So he's basically saying I'm only going to use inertial reference frames, and that was his way of cutting out gravity. Because if you look at an object falling, you'll see that it's actually accelerating, and you don't see any obvious force acting on it. So that's a clear violation of Newton's law of inertia, or Galileo's law of inertia, or Newton's first law of motion. So as I told you, the mass has a unit of a kilogram in the SI. In the CGS, it's the gram. And in the British system, it's the slug. The unit of force, on the other hand, turns out to be from Newton's second law, force is equal to mass times acceleration. So you take the unit of mass and multiply it by the unit of acceleration, and you get the unit of force. In the CGS, that's the gram times the centimeter per second squared, and that's called a dyne, D-Y-N-E. In the SI system, which is what we're going to use in this course, it's the mass times the acceleration. So that's a kilogram times a meter per second squared. That's called a Newton. And a Newton is about 2.28 pounds, or excuse me, 2.228 pounds. So it's not a very big quantity. Let's put it that way. Or actually, I should say 1 Newton is about 0.228 is what I was trying to say. I don't think I said that correctly, so I just wanted to point it out. It's a little bit less than a quarter pound. 0.228 is a little bit less than a quarter pound, which would be 0.25. Another way of looking at it is 1 pound is 4.45 newtons. That's another way of looking at it. Okay. And then in the British system, the unit of force is also the mass times the acceleration. In that case, the mass is the slug and the acceleration is feet per second per second. So the slug foot per second, or the slug foot per second squared, is a unit called the pound. Okay. Mass is a property of an object, a measure of the object's inertia, for instance. Weight, on the other hand, is a force, the pull of gravity acting on an object, for instance. So if an object is on a planet, then it's the force that the planet has as an attraction for that object, and that's called the weight. If it's on a moon, then it's the force caused by that moon. If it's on a big asteroid, then it's the force caused by that asteroid. However, if it's on an asteroid at which you're close enough to a planet so that the planet has a bigger force, then you'd probably call the force of gravity the force that the planet's causing, and the force of gravity from the asteroid a different force, but you wouldn't call it a weight. All right, now that we've got all that and we've talked about all that, we're going to move on to another example because we've covered all the laws of physics. I've highlighted, by the way, these units, the SI units for the Newton, the pound, the British unit, of course, for the pound, the CGS unit for the dyne. I've highlighted all those and shared those notes in your textbook so you can see them. But let's go on to example 4.2, which is an estimate example. So example 4.2 says estimate the net force needed to accelerate a a 1,000 kilogram car at 1/2 of g. And what we want to know is the summation of the forces is equal to question mark. And then part B, a 200-gram apple at the same rate. So a 200-gram apple at 1/2 g, the summation of forces is equal to 0. So solution, I want to point out the law of physics that I'm using here, and that's Newton's second law of motion. And I said that, and hopefully you looked at it in your book, but just in case you didn't, here's the way I wrote it, or I said it in defining it. The acceleration of an object is directly proportional to the net force acting on the system and inversely proportional to the mass. This is equivalent to saying the summation of the forces is equal to mass times acceleration. Now remember, these are vector equations. When you have a vector equation, that means the left-hand side has a magnitude and the right-hand side has a magnitude, and the left-hand's magnitude has to equal the right-hand's magnitude. Additionally, the left-hand side has a direction and the right-hand side has a direction, and those have to be equal as well. Or you can't say, you can't put an equal symbol between two vectors if that's not the case. Okay. So with that in mind, you can see now that I have the summation of the forces. So you add up all the forces that are caused by anything other than the mass M and are acting on the mass M. That's what the summation of the forces is. So all the forces acting on the mass M caused by anything other than the mass M is what goes on the left-hand side. The mass M is the mass of the object or the system that you're studying. And then the acceleration is the acceleration of the center of mass of that system, which for right now, we're pretending everything's going to be like a point particle. So the center of mass is really the position of the mass. Now that we have that, we can go ahead and say exactly what is the total force. So for part A, F equals, and here's the wording, it's the net external force. That's what the summation of forces means. In some cases, that could literally mean it's a single force. Okay, there's not more than one force acting on it, and that's just fine. But in that case, there's only one force acting, so the summation only goes from I equal 1 to 1. So you only have to do one term, and that's what's going on there. The other thing is to remember that by the equation A equals the summation of forces over the mass, the summation of the forces is a vector quantity and therefore has a direction. If you divide that by mass, that mass, which has to be positive, will not change the direction of the force at all. Remember, that's what we learned when we multiply a scalar by a vector. It can only change the direction of the vector if the scalar is negative, and when it is, it changes it by 180 degrees. But when it's positive, it doesn't change its direction at all. So Newton's second law not only tells us that the acceleration is directly proportional to the net force and inversely proportional to the mass, it also tells us that it's parallel to the net force. All right. So F net equals external force. In this case, we're going to say 1,000 kilograms is the mass times the acceleration is 1/2 g. So I'm going to put 1/2, and then g has an acceleration of 9.80 meters per second per second. So you can see that it's going to be 1,000 times 4.90 basically. So zero point 0.5 times 9.8 is 4.9. And then you multiply that by 1,000, that's 4,900. And the unit is a kilogram meter per second squared, which is defined to be 4,900 newtons. 1 Newton is defined to be 1 kilogram meter per second squared. Okay, so that's our net force required to actually accelerate a car at 1/2 of gravitational acceleration. Now, technically speaking, I worked all that in terms of scalars, but because I did that, it's really not appropriate for me to put that arrow over the F. So now I just wanted to point that out so we know exactly what the net external force is. I'm going to say it's now the magnitude, and I'm going to get rid of that. And the way I'm going to do it is I'm going to put absolute value bars on it, because now the absolute value bars around the net external force means just the magnitude of the force. Now, we only had probably one sig fig there, the 1,000. That's what your author calls an ambiguous number of sig figs. So it's no more than, it's probably one, but it could be in principle four. So your book is rounding this to 5,000, and that's certainly fine. Now for part B, they want us to find the same quantity And this time they want it for the 200-gram apple. And of course, if we're using it in grams, then that would be the CGS system and that would come out in dynes. I don't necessarily want that, but let me show you just so you know. It would be 200 grams times 1/2 of gravitational acceleration. Now remember, the gravitational acceleration is in centimeters per second in the CGS system. So that means the acceleration is 980 centimeters per second. And this automatically gives me dynes, which is a really small quantity. So I take 200 times zero point 0.5 times 980, and that gives me 98,000 dynes. Well, let's take a break here and write grams centimeters per second squared, which equals 9.8 times 10 to the fourth dynes. So that is technically an answer. It's not the answer we're going for, but I wanted you to have some experience understanding that when you're working in the CGS system, the acceleration due to gravity is 980 and it's in centimeters per second, not in meters per second. Now, to do it more correctly, the way we're supposed to be doing it in this class, it's still summation of forces equals mass times acceleration, but now it's going to be 0.200 kilograms times 1/2 times 9.80 meters per second. And that's going to come out to be newtons. So I can say zero point 0.2 times zero point 0.5 times 9.8. And we get that that is 0.98 newtons is equal to the summation of the forces. So that's the unit and the answer for part B. Anybody have any questions on that? All right, let's look at another example. This example is example 4.3. Example 4.3 says force to stop a car. What average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour? Excuse me, within a distance of 55 meters. So we're asking what average force. So I'm going to say F bar is equal to question mark to bring a car of mass M equals 1,500 kilograms and its initial velocity V initial is equal to 100 kilometers per hour, which we need to go ahead and convert to meters per second. And remember that basically means dividing by 3.6. Let me show you why. 1 kilometer is equal to 1,000 meters. And that, of course, gets rid of our kilometers in the top and replaces it with meters in the top. And then 1 hour is equal to 3,600 seconds. So that gets rid of the hour in the bottom and replaces it with seconds. Notice I'm taking 1,000 and dividing it by 3,600. That means we get divided by 3.6. So 1,000 divided by 3.6 is equal to 27.78. Oops. And the final velocity, V final, is 0 meters per second in delta x because it said within a distance. And remember, distance is initial position minus final position, at least in terms of displacement. And if the object's going in a straight line, the distance traveled is the same thing as the displacement. So that's okay. So I'm calling delta x to be 55 meters. So in order for us to calculate this force, we need solution. We need the summation of the forces is equal to mass times acceleration. That's the vector equation. But in order to do that, we're wanting the F, which is just one of the forces, and hopefully it's the only force. That's what we're trying to calculate. But in order to get the F, we need the mass and the acceleration. So I need an equation that would give me the acceleration. So this is the first example for you guys to see that how a physics course is always comprehensive. When we get to chapter 4, we're still doing stuff from chapter 1 and chapter 2 and chapter 3. So in this case, we're going to use v squared is equal to v0 squared plus 2a x minus x0. And this quantity is what I'm calling delta x. So I can use that to get the acceleration. I can then plug in the acceleration into F equals ma, and that'll get it for me. Now, because this is a vector equation, I should take the time to point out that it can be broken down into the summation of forces in the x direction equals mass times acceleration in the x direction. The summation forces in the y direction equals mass times acceleration in the y direction. And the summation forces in the z direction equals mass times acceleration in the z direction. Those are three scalar equations that are equivalent to that one vector equation. And it's normally what you use. It's very rare that you get to use the full vector equation, at least in F equals ma. But these things have quantities that can be positive or negative because they're not magnitudes, they're components of vectors. So the a sub x is a component and it can therefore have a negative value. And the f sub x is a component of a force, so it can therefore have a negative value. So, with all that being said, we're imagining the car moving along the x-axis, say, in the positive direction or whatever, and it's going from a very high velocity to a very small velocity. And using v squared equals v0 squared plus 2ax, we can find that v squared minus v0 squared over 2 times delta x is in fact equal to acceleration. So that allows me to calculate the acceleration is 0 squared minus 27.28 meters per second quantity squared. Now we only had 3 sig figs at most there because they gave us 100 kilometers per hour. So I'm going to underline that 8 there. All of that's going to be divided by 2 times delta x, which is 55 meters. So I'm basically taking 27.28 and I'm squaring that, and then I'm dividing it by parentheses 2 times 55, close parentheses. That gives me negative 6.765 meters per second every second. So negative 6.765 meters per second every second. We only had 3 sig figs, so the 5 is not a sig fig. Now that we have that, we can say the summation of the forces is really just one force, and that's going to be equal to mass times acceleration. So that one force should be equal to 1,500 kilograms. Now, I'm dropping the negative because the negative is all about, in this case, since we're going in the positive direction, it just means the acceleration pointed in the negative direction. So the force would be in the negative direction. We don't really care about that. We know what direction to apply it. If we're trying to slow down a car, we're going to push from the front towards the back. So I'm just going to put the number in here and not worry about the sign. And that's 6.765. Notice this velocity, or excuse me, this acceleration calculation that we did, that was an intermediate calculation. Our goal was to calculate the force. It wasn't to calculate the acceleration, but we couldn't get the force without the acceleration. So as I told you, whenever you're doing intermediate calculations, you always want to carry at least one extra digit beyond the sig figs. I always carry at least one, but sometimes I carry 2, 3, 4, or however many my calculator spits out. So with that in mind, I'm not multiplying it by the rounded version of 6.765. I'm rounding it by the full version. So when I multiply that by 1,500, I get 1.015 times 10 to the fourth. And you see the unit is a kilogram meter per second squared, which is a Newton. And of course, it's got one extra digit that's not a sig fig. So I underline that digit, and now we can see that that is the actual force required to stop this car. Anybody have any questions on that? Again, you could make note of the fact that the acceleration was negative and then call the force a negative because it just means that it's acting in the negative direction. But in this case, I just asked for specifically, or the question just asked for what average force is required. Okay, that's it. Any questions on that? All right. So we'll move on. Your book gives a precise definition of mass. That's sort of important for you to read, but just carry on after that. And you're going to go into the section where they talk about Newton's third law, which I've already told you. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction. That is called Newton's third law of motion. For every action, there's an equal but opposite reaction. And the big thing to remember here is the two forces that have the same magnitude are action reaction pairs only if they're reversed. So it's important that I said Newton's third law. Let me write it down here at the bottom of this tablet. I'm going to write Newton's third law in the way that I was saying it earlier. Newton's third law says F12 is equal to negative F21, but I can't just do it like that. I actually have to have the vector symbols above it. It's saying the force on object, oops, I put that C too close to that T. The force on object 1 due to object 2 is equal in magnitude, but opposite in direction of force on object 2 due to object 1. So the force on object 1 due to object 2 is F12, and that's equal to the negative of the force on object 2 as a result of object 1. That's the key thing to understand is the two objects have to be opposite. So for instance, if you say, what's the action reaction pair with the force of gravity pulling me down off of a curb? Then you'd say the force that's pulling me down off of a curve is my force, mainly my weight, let's say 250 pounds. And the action reaction pair to that is me pulling up on the earth. The earth pulled down on me. That's what caused gravity. So the force on me of 250 pounds is the force of gravity as a result of the earth. So it's the force on me as a result of the earth. So the force of the earth as a result of me is the 250 pounds pulling up on the earth. Notice how they reversed? It went me and earth and me. That's the key. If you don't see that they're opposites, in the opposite order, then they can't be action reaction pairs. So just keep that in mind. All right, now we'll carry on to some more examples. So let's look at a conceptual example 4.4. This was a conceptual example, so it's more or less just going to be me explaining it, but it says, what exerts the force to move a car? What makes a car go forward? That's the question. Now, your book gives a long, it's a paragraph roughly, but I want to explain it to you so you have some slightly better understanding. And it might even let you understand why Newton's third law of motion is so important. But basically, when a car accelerates, what you're doing is you're sitting in the car, say, and you're putting your foot on the accelerator. You push the accelerator, that actually causes the engine to bring more gas to the individual pistons, and that ends up causing the pistons to fire a little bit more rapidly, and therefore the engine camshaft and all that stuff is going to turn a little more rapidly. All of that's going to go into the transmission, and then the transmission is going to adjust the rate at which the engine rotates to match the rate at which the drive shaft should rotate, and then that drive shaft is going to run into the differential. The differential is going to relate the rotation of the drive shaft to the rotation of the axles, which obviously, when you go around a curve, have different speeds because the inner tire has to go slower than the outer turn tire when you're making a turn. So that differential, that's why they call it a differential, is because it's doing a differential velocities between the two. They're going to attempt to turn the wheels this way so that the car will take off. So all of that is happening when you hit the accelerator. And then the accelerator is trying to turn the wheels, which of course are attached to the tires, and therefore the tires are going to rotate in a forward direction, meaning the top of the tires are going to head towards the front of the car, and the bottom of the tires is going to head towards the back of the car. And when you do that, if there's not sufficient friction, they're just going to spin out, which you've seen probably in drag races and stuff like that, or just people playing around or power braking or whatever. But what really happens is if there's enough friction, then the transmission and engine and all that stuff is trying to force those tires to rotate forward, but the friction force between the road surface and the tire is big enough, so it's going to actually apply a force in the forward direction to the bottom of the tire that's just enough to counteract the force that the engine has applied to the tire at that particular point. And in fact, according to Newton's third law, the force that is applied by the tire to the road is going to be equal in magnitude but opposite in direction to the force applied to the tire by the road. So the engine applies a force to the tire and it tries to turn relative to the road, but Newton's third law kicks in and makes the bottom of the tire experience a force equal in magnitude but opposite in direction to the force that the tire was trying to impart in onto the actual road. So ultimately, Newton's third law is really way more important than you thought because even if you knew exactly how much force your engine could put out when you hit the accelerator at a certain amount, you still couldn't calculate what the acceleration of the car would be because you don't. It's not that you need the force that the car puts on other things. You need the force that the earth puts on the car. And the force that the earth puts on the car is given to us by Newton's third law. So you can see you can't really do much with Newton's second law in many cases unless you already know Newton's third law. So hopefully that conceptual example gives you a little bit better feel. It's a little bit more convoluted, but that's sort of the whole point. When you really start to understand things, they're a little more complicated than you might think. So make sure you read that response. Watch back over this video to see my response. Hopefully I didn't, flub too many words or whatever. I'm sure I've dropped a few in there or something, but either way, just keep that in mind and ask me if you don't understand as well. So now we'll go to a conceptual example 4.5. It says Michelangelo's assistant has been assigned the task of moving a block of marble using a sled. See figure 412. He says to his boss, when I exert a forward force on the sled exerts an equal and opposite force backwards. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force, so the net force must be zero. I'll never be able to move this load. Is he correct? Okay. a lot of things he's saying there are true, but you've got to remember that action reaction pairs act on different things. That's part of the reason that I showed you Newton's third law in that equation form. F12 is equal to negative F21. That means the force on object 1 as a result of object 2 is equal in magnitude but opposite in direction to the force on object 2 as a result of object 1. So notice F12 is acting on 1 and F21 is acting on 2. So in this case, when he says, when I exert a forward force on the sled exerts an equal and opposite force backwards. Yes, when he applies a force of 100 newtons, let's say, to the sled applies a force of 100 newtons backwards on him, but the force on him is irrelevant to the total force on the sled. The total force on the sled is what matters in terms of calculating the actual acceleration of the sled. So his mistake here is misunderstanding the idea that the Newton's third law is actually telling about two different forces acting on two different things, and there's no way those two forces are ever both going to be on the left-hand side of Newton's second law. Newton's second law has the summation of the forces on mass m on the left-hand side is equal to the mass m times the acceleration on the right-hand side. The only forces that can be on the left are the forces on m, not the forces m applies to other stuff, which is what's happening here. Any questions on that? All right. I want to take a second to use Newton's second law to derive what weight is. So you'll have some idea of what we mean by weight. I've been telling you that weight is a force quantity. I've been telling you that mass is a scalar quantity. I told you that the unit of mass in the SI system is the kilogram, and in the British system it's the slug, and the CGS it's the gram. And I told you that the unit of force in the SI system is the Newton, in the CGS system is the dyne, and in the British system, it's the pound. But now I need to show you how you actually find out what that, in this case, that specific force called the weight is. So we'll go back to our understanding of free fall. So remember in free fall, which we studied first in chapter 2, and then we use that in chapter 3 as well. In free fall, what we have is an object like a ball, and that object only has acting on it the force of gravity. In other words, we ignore air resistance specifically. So the force acting on this is the force of gravity, and the force of gravity is what we call the object's weight. Okay, that's the only force acting on it. Now, according to Newton's second law, the summation of the forces acting on an object, this object has a mass m, by the way, is equal to the object's mass times the object's acceleration. Now, does anybody recall what the acceleration is for an object in free fall? It had an acceleration equal to g in magnitude, like Michael said. And normally we treat the upward direction as positive, the downward direction as negative, in which case you'd call it negative g, and that's certainly acceptable as well. We're just going to use the actual magnitude of it. So what we can say is applying Newton's second law. Oops. And applying Newton's second law, we're going to say the summation of all the forces is equal to mass times acceleration. We just discovered that the total force acting on it must be equal to the weight. The object's mass is just m, and the acceleration is just g. So, lo and behold, this is our formula for the weight. So whenever you're on, or whenever some object is on a heavenly body of some sort, whether it be an asteroid, a comet, a moon, a star, a planet, or whatever, and obviously there's some problems with certain planets with an object being on it, or with stars, of course, there's a big problem with something literally sitting on a star. But the main thing is, if you need to know the object's weight, you're going to have to figure out what the gravitational acceleration is for that particular altitude, for that particular heavenly body, and that on Earth is what we call G. And if you take that G and multiply it by the mass in kilograms, you'll get the weight in newtons. For instance, we often assume the acceleration of gravity is pretty close to 10 if we just want a quick order of magnitude calculation. So you can sometimes just say 10 times the mass is pretty much what your weight is. It's technically got to be 9.80. And of course, it's technically got to change. For instance, if we go to the bottom of the Marianas Trench, it's going to be about 1% higher than 9.8. Or if we go to the top of Mount Everest, it's going to be about 1% smaller than 9.8. But either way, that's the way you calculate the weight is you multiply the mass times the gravitational acceleration. Any questions on that? Now, if you just look at something like right now, your book has this bust of Abraham Lincoln sitting on a tabletop. So if you look at a bust, a statue, if you will, of the head of Abraham Lincoln sitting on a tabletop, you look at it and you realize, okay, according to Newton's first law of motion, this object is not moving, so the net force acting on it must be zero, right? Because Newton's first law of motion says an object will move with a constant velocity in a constant direction unless the net force is non-zero. In this case, the object is moving with a with a constant velocity. Specifically, the velocity is zero, right? Because of that, we know the acceleration is zero. And because the acceleration is zero, we know that the net force is zero. But in looking at this bust of Abraham Lincoln sitting on a table, you can figure out that there's at least one force acting on that bust, and that is the force of gravity. So when I draw a free body diagram, for instance, of Abraham Lincoln's bust, so I know it's a little goofy to say Abraham Lincoln's bust like that, but I'm going to attempt to draw Abraham Lincoln to some extent, and I'm going to take out my hatred in him by pointing out that he has way better hair than I did, even though he died at such a young age. That's a little disappointing to me. And give him big googly eyes. Okay, this is his head sitting here, and he's sitting on a table. So there's the statue, if you will, of it. Now, the free body diagram that we use FBD, you normally treat an object as a point. Once we learn about torque and center of mass, we can stop calling it a point object and pretend it actually has a physical structure. But until then, we're always going to pretend the objects are characterized as a infinitesimally small point. So this is the bust, this little purple dot here. And acting on it is the bust's weight, W, which equals m times g. And we know that the acceleration is equal to zero, and that implies that the summation of the forces must be equal to zero as well. So there's one force, and we know that force can't be zero, yet the total force acting on it is zero. So that tells us we have to have at least one other force. The other force has to be equal in magnitude but opposite in direction in this case because they have to add together to give you zero. So that other force is what we call F normal. So we put a F and then we put a subscript N on it. The N means normal, which is the correct geometric term for something being perpendicular to a surface. So you'd say perpendicular or orthogonal. Those are words that quote unquote sort of mean the same thing. Normal's another one that sort of means the same thing, but none of them actually really mean completely the same thing. Orthogonal has a very specific definition. Normal has a very specific definition, and perpendicular has a very specific definition. But the main thing here is since the summation of forces must be zero, then that tells us that Fn minus mg Fn minus mg must be equal to zero. And that's what it is. It's called the normal force. And it might seem weird to you. We have an inanimate object, a table, and it's applying a force to a statue. That might seem a little weird, but think about it this way. Imagine that the table's not necessarily being so active. It doesn't have a conscience and it's not saying, okay, I need to go 9.8 times 3.2 kilograms and then apply that force to this thing because that's how much it weighs. It's not doing all that. It's made of a specific shape so that it maintains a specific geometry and it's going to be in that shape. When you apply a force to it, that force is not necessarily interacting with the table other than the table holding it up. And if you were, for instance, to replace this bust of Abraham Lincoln with, for instance, a elephant, you would quickly see that the table would be insufficient to hold up the elephant and the elephant would just completely break through it. So what happens is when you make a table, for instance, or a bar or a surface of any sort, it has a certain amount of strength, a certain capacity to hold up a certain amount of stuff. And when you put something on it, it's going to give as much of that that it possibly can to try to hold it up without bending itself. So that's really what's going on. The normal force is the force that's perpendicular to a surface, and we know it has to be there because Newton's first law dictates it's got to be there. Does everybody understand where we got the normal force from? The force a surface applies to an object on that surface the force a surface applies to an object on that surface is perpendicular, and I'm using perpendicular because that's a word you're more familiar with, is perpendicular to that surface and it is called the normal force, which we normally indicate by F sub n. Sometimes your book and other authors might just say n. I usually say F sub n. Okay. So that's what our normal force is, and that's going to come in really handy. For starters, it's the force that you got to calculate if you're, for instance, designing a roof or a floor of a house. For instance, when you actually build a house, you'll have these beams that run one direction, and then perpendicular to those directions are joists, which are meant to hold up the floor. And code says that you have to allow 35 pounds per square inch for the floor plus the material, and it can't sag but a certain amount, and therefore you have to calculate what are all the forces on it, and then make sure that if I use 2x4s or 2x6s or 2x8s or 2x10s, and you never use 2x4s by the way, whatever you use there, you've got to make sure that they're going to be able to supply a sufficient amount of force, or else the building inspector is going to come in and say, okay, you got to rip all that out and redo it, or you're just going to have to stop building everything. Okay, so the normal force is really the force that the surface has to supply, and that's what we're calculating when we design rafters, for instance, to hold up a roof, or when we design joists to hold up a floor, or when we design studs, for instance, in a wall to hold up a roof. So all of that stuff comes in handy. Now that we have that, let's look at example 4.6. A friend has given you a special gift, a box of mass 10.0 kilograms with a mystery surprise inside. The box is resting on a smooth, frictionless, horizontal surface of a table. A, determine the weight of the box and the normal force exerted on it by the table. B, now your friend pushes down on the box with a force of 40 newtons, as in figure 415b. Again, determine the normal force exerted on the box by the table. And then C, if your friend instead pulls up on the box with a force of 40.0 newtons, what now is the normal force exerted on the box by the table? So this is example 4-6. I'm going to write down the information we have. We have the box, which has a mass of 10.0 kilograms. And then we are to A, determine the weight of the box, which equals question mark, and the normal force, which equals question mark. And then with part B, we're going to add a force F1 is equal to 40.0 newtons downward. And we're going to calculate now what is the normal force. And then for part C, we're going to pull up on it with a force F2 is equal to 40.0 newtons. And again, we want to know the normal force is equal to question mark. Now, forces are generally vector quantities, but when we're deciding them in one dimension, you can just talk about their magnitudes. That's why I haven't been using all the arrow symbols and stuff like that. Now, let us begin solving it. Our solution is going to require us to use the formula for weight. Weight is equal to mass times gravitational acceleration. It's also going to require us to use Newton's second law of motion, which tells us that the total force acting on an object, the summation of forces, is equal to the mass multiplied by the object's acceleration. We're going to make use of that as well. So first off, for part A, I'm going to draw a free body diagram. Again, the word I'm saying here is free body diagram, and it's one of the single most important things that you need to learn from physics 241, from physics 1 basically. So you've got to draw it. It's normally until you get to covering torques and stuff like that and center of mass, until you get that, you're going to actually treat the objects as if they're point particles. But then your job is to go ahead and decide on coordinate systems and show all the forces. So what I'm going to draw is a coordinate system, and there are ways you can do physics without drawing coordinate systems. I just find them very comforting. So I'm going to draw an x coordinate system and a y coordinate, or an x axis and a y axis, such that the y axis is positive pointing up and the x axis is positive pointing to the right. Right at the origin, I'm going to draw the object of mass m equals 10.0 kilograms. And now I'm going to show the forces acting on it. The forces acting on it are the gravitational force, which is the weight, and that acts in the negative direction. So I'm going to draw that with a red arrow. That is weight is equal to mg, which is 98.0 newtons. And then there's a force acting upward, which I'm going to draw with green because, red is stop for a stoplight and green is go for a stoplight. So I'm going to say red is the stopping color and green is the positive color. This force right here is the normal force, and that's what they're asking for in addition to the weight. We've already calculated the weight is 98.0 newtons. So we have that. I can say weight is equal to m times g, which is 10.0 kilograms times 9.80 meters per second, which equals 98.0 newtons. And that's equal to the weight. And I'm going to circle that off because that's part of the answer for part A. Now, the other part is the normal force. Well, If we take Newton's second law, remember Newton's second law is a vector equation, but it's represented by three separate scalar equations: the summation of forces in the x direction, the summation of forces in the y direction, and the summation of forces in the z direction. So the summation of the forces, let's go back to green, sorry about that. So Newton's second law becomes the summation of the forces in the x direction equals mass times acceleration in the x direction. The summation of forces in the y direction equals mass times acceleration in the y direction. And in this case, the object's sitting perfectly still. It says a friend has given you a special gift, a box of mass 10.0 kilograms with a mystery surprise inside. The box is resting on a smooth, frictionless horizontal surface. Since it's resting, that means it's not moving. Its velocity is zero, and its velocity is still zero, and its velocity is still zero. So the acceleration is zero. And that means, of course, that a sub x is equal to zero and a sub y is equal to zero. In the case of a sub x, there's no other forces acting in the x direction, so there's no reason to attack that. But we do have two forces acting in the y direction, so I can translate that into the summation of the forces in the y direction is equal to mass times acceleration in the y direction, which we just said was zero. And from that, we get F normal minus the weight, W, is equal to zero. And that means the normal force is actually just equal to the weight, which equals 98.0 newtons. So that's how we get the normal force. We use Newton's second law in the y direction. And in this case, the acceleration in the y direction was zero. So the normal force had to be such that the normal force plus the weight, which, by the way, I wrote it minus, it's still summing on the left hand side. But what I was really doing was adding a negative quantity because the component of weight in the y direction was negative. So it's plus a negative. I'm just not willing to waste all the time to write plus a minus number, plus a negative number, when I can just write minus. So just keep that in mind. The left-hand side of Newton's second law is always a sum. It's never a subtraction. Okay. It turns into subtraction when one of the quantities has a negative magnitude. Or a negative component. That's the main thing. So now we've got that. Now we can do part B because you've seen a little bit from part A. So for part B, we're going to have, again, a coordinate system. And this time, we're going to have a mass of 10.0 kilograms. We're going to have a force in the upward direction of Fn. We're going to have a force in the downward direction of W equals 98.0 newtons. And because in part B, they said now your friend pushes down on the box with a force of 40 newtons. So we have another force in the downward direction that I'll draw right here, and that's going to be called F1 is equal to 40.0 newtons in the downward direction. Notice I didn't write the 98 as negative and I didn't write the 40 as negative. I indicated that by showing the red vector. Okay, you could write it there, that's fine. The main thing is you got to remember it's negative when you put it in F equals ma. So now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction, and the fact that the acceleration in the y direction is zero, and that's going to give me the Fn minus 40.0 newtons. Remember, that's technically plus negative 40. And again, this next one's supposed to be plus negative 9.8, or excuse me, negative 98, but I'm going to write minus 98.0 newtons is equal to zero. So from that, we get that the normal force is 98 plus 40. That should be 138.0 newtons is the normal force. And that's our answer for part B. Everybody see how that happened? All right. Now for part C, again, coordinate system. If you draw the arrows on one end, then I'll understand that that means the positive, and the other end would be the negative, of course. So we have the same thing here, 10 kilograms. We're going to have a normal force acting in the upward direction, F normal. We're also going to have a force in the downward direction, which is the weight, W equals 98.0 newtons. But in this time, in part C, it says your friend instead pulls upward on the box. So now our friend has applied a force F2 in the upward direction, where F2 is equal to 40.0 newtons. Now I take the summation of the forces in the y direction equals mass times acceleration in the y direction. And that gives me Fn plus 40.0 newtons minus 98.0 newtons is equal to 0. So in this case, we get N is equal to 98.0 newtons minus 40.0 newtons, which equals 58.0 newtons is the normal force, and that's our answer to part C. So you can see the normal force always has to be perpendicular to the surface. And it's often the weight of the object, but you can see in some cases it's not going to be the weight. And in fact, when we start talking about tilted surfaces, it's going to be entirely different. So we're going to work, for instance, on inclined planes and stuff of that sort. And there's a different calculation that goes in there. And I'll teach you how to do that. But right now, we just have to remember that the normal force is always exerted by a surface on which something is resting, and the normal force is perpendicular to the surface, and it has to be calculated by using Newton's second law and combining all the forces acting in that direction perpendicular to the surface. Any questions on that? All right, so now let's look at example 4.7. So example 4.7, accelerating the block. Accelerating the box. What happens when a person pulls upward on the box in example 4.6c with a force equal to or greater than the box's weight? For example, let Fp equals 100 newtons rather than 40 newtons shown in figure 415c. Okay, so they're asking specifically what happens when a person pulls upward on the box with a force equal to or greater than the box's weight. So I'm going to start off with a free body diagram again. There's my x-axis. There's my y-axis. Here's my mass, which equals 10.0 kilograms. Here's my weight, which points downward. W is equal to 98.0 newtons. And then the force we apply upward will be what we call F sub P. Okay, like that. So, what happens when a person pulls upward on the box with a force equal to or greater than the box's weight? Let's examine the two cases. First, what if Fp is equal in magnitude to the weight? Well, in that case, we have the summation of the forces in the y direction equals mass times acceleration in the y direction. We don't know what's going to happen, so I can't just blindly say that the box is resting and therefore the acceleration is zero. I don't know that. So in this case, what I'm going to do is I'm going to write that the force is equal to the weight. So I'm going to say it's Fp minus W is equal to 10.0 kilograms times A. Now I can put in the fact that Fp is supposed to be equal to the weight, so that's 98.0 newtons plus negative 98.0 newtons. That's what's really happening every time it's plus a negative. I just thought this would be a good time to write that in. And that's equal to 10.0 kilograms times A. But you see that 98 plus negative 98 is 0 newtons, and that's equal to 10.0 kilograms times A. Therefore, A is equal to 0. And that means when the normal force is exactly equal to the weight, then there's zero acceleration. In this case, we're actually pulling up on it with a FP. Uh, in reality, though, you could also look at this as a normal force option. So let me show you what happens when we're doing this in terms of a normal force as well. It's sort of the same thing, but I just want you to understand what's going on in terms of the normal force. So here's the X, here's the Y, here's the mass. 10.0 kilograms. The force acting downward is 98.0 newtons. The force acting upward, oops, I should have drew that in green. The force acting upward is F sub P is equal to 98.0 newtons. And then there's another force acting upward, and that's the normal force like that. So what you end up getting with the summation of the forces in the y direction equals mass times acceleration in the y direction, we get Fp plus Fn plus negative W is equal to m times A. Now, if I put these values in, I get 98.0 newtons plus Fn plus negative 98.0 newtons is equal to 10.0 kilograms times A. And you can see that when the total force on the left-hand side that you can add, the 98 plus the negative 98 gives you 0, then the Fn is the only thing left to accelerate it, but the Fn doesn't have the ability to accelerate anything. Okay, it's just I want to say I'm actually losing a word here. It's sort of a non-player. It doesn't actually interact with the universe around us. It just does what it can up to some limit. But there's never going to be a time where the normal force makes something jump off of a table. Right? If the table were to move up, then the normal force could actually force the object to move up in that case, but that's because someone lifted the table. So in this case, what we get is the normal force is equal to 10 kilograms times, or excuse me, 10 kilograms times A. And since the normal force is only as big as it needs to be, the normal force is 0. And the acceleration equals 0. So this is when Fp is equal to W. So our results when Fp is equal to W is that the normal force becomes 0 and the acceleration is 0. Now we're going to handle the other part, which is what if the Fp is greater than the W? Okay, so in this case, I'm going to draw another free body diagram. There's our y-axis. There's our x-axis. There's our 10.0 kilograms. Our weight is 98.0 newtons. Our FP is equal to 100 because that's what they specifically suggested we say it is. It was 100 newtons. And then, of course, we also have a normal force acting Fn like that. Okay. So that again, it seems kind of weird in both the first diagram we did, or excuse me, the second diagram we did, and this diagram to include the normal force. At least it felt that way to me, and I thought it would feel that way to you. That's why I didn't put it there initially, because you know that when the force is equal to the other one, it's the normal force isn't going to be required. But just to argue exactly what happens to the normal force, we need to do this. So now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction without making any assumptions about the acceleration in the y direction. I'm going to get 100.0 newtons plus Fn minus 98.0 newtons is equal to 10.0 kilograms times A. Therefore, you get 2.0 newtons plus Fn is equal to 10.0 kilograms times A. So you see here that the FP is so big that it completely wiped out the weight of 98 newtons and left us with a result of 2 newtons acting upward. So there's no need for the normal force. Therefore, no need for Fn. Therefore, Fn is equal to 0. So we now have 2.0 newtons is equal to 10.0 kilograms times A, which means A is equal to 2.0 newtons divided by 10.0 kilograms. Remember, a newton is a kilogram meter per second squared. So if I divide a kilogram meter per second squared by a kilogram, then all I get is a meter per second squared, and that's going to be 0.20 meter per second, and F normal is equal to 0 when FP is equal to 100.0 newtons. So this is our answer to this part. So when you apply a force upward pulling on it that's greater than the weight, then the normal force becomes 0 as well, just like it did when it was equal to it. But in this case, it's going to actually accelerate it, and you don't have to. There's never a time where the normal force is going to cause it to be to act in a downward direction to try to keep it from leaving or anything like that. The only way that could happen is a little bit of maybe a decrease in pressure between the bottom and the top of the table and the bottom of the object, the box, or perhaps gravitational attraction between the box and the table, but that's such a small force it wouldn't matter. So, anybody have any questions with that for that one? All right, let's move on to example 4-8, and this one's kind of neat because now we're going to move, imagine a elevator car. So example 4-8, apparent weight loss. A 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g. Watch out when they say 0.20 g, they're not talking about grams, just like they didn't in the previous one when we said 1/2 g. They're talking about gravitational acceleration. Okay. So it says a 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward. She stands on a scale that reads in kilograms. During this acceleration, what is her weight and what does the scale read? Part B, what does the scale read when the elevator descends at a constant speed of 2 meters per second? So this is really, really, really a good question. This is example 4-8. Okay. What we have is the woman's mass is 65 kilograms. And we have that the acceleration of the elevator when it occurs is 0.20 times g, which equals 0.20 times 9.80 meters per second. And of course, that would be 1.960 meters per second. And of course, we only had two sig figs, so I have to underline those two. So that's the acceleration. Later, we're going to have a velocity of the elevator equal to 2.0 meters per second. And we want to know, what does the scale read Now, scales normally measure force, so I intend to call it F scale, but they're saying the scale reads in kilograms, so it's really the M of the scale. So uh, let's correct that by instead of saying F scale, we'll say M scale is equal to question mark, and I'll put a kilogram in parentheses just to remind us that's in parentheses or that it's in kilograms. Okay. So for part A, they want to know what is the M scale. So I just moved it over to the left there. And then in part B, they want to know the same thing, M scale, when A of the elevator equals 0, but V of the elevator is equal to 2.0 meters per second. And I should say this is downward. So the acceleration is going to be downward. Now, in principle, what we have here is an elevator. And the way I normally draw a scale is I do something like this, and then I'll put a platform on it, and then I put a person right here like that. That's the actual picture of what's happening. Okay, and we know that that scale reads in kilograms, but now I need to translate that into a free body diagram. So with our free body diagram, there's my x-axis and this is my y-axis pointing up here. I'm going to take a mass of 65 kilograms and draw it right there. Now, acting on it will have a weight. So gravity is going to be pulling that 65 kilograms downward. And that weight is M times G, which is 65 kilograms times 9.80 meters per second. If I take 65 times 9.8, that gives me 63, or excuse me, 637.0 newtons. We only had two sig figs, so the 7 and the 0 are not significant. Now, in addition to that, we have a force in the upward direction, which is the force due to the scale. Okay. Now over to the side, because in engineering, some teachers will teach you to include an acceleration in a free body diagram, or they actually make an acceleration diagram and a force diagram too. We try not to do that, but I do sometimes remind everybody that when there's an acceleration, I'll just put it off to the right, and this acceleration is actually in the downward direction. So I'm going to say A is equal to 2.0 meters per second for part A. So that's what we're doing here is part A, and I should have written that in purple, but I didn't, so oh well. Now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction. And with that, I can see that I have the force on the scale, which would come out in newtons, by the way. So I've got to then divide it by 9.8 to get the mass that the scale would read. But we still have a force being applied by the scale. That force acts in the upward direction. The weight acts in the downward direction. So that's going to be minus 637.0 newtons. That's the two forces acting on it. And the object is actually has a mass of 65 kilograms, and it actually has an acceleration downward. So that acceleration is negative 2 point, or excuse me, negative 1.960. I don't know. Oh, I took the velocity. Make sure y'all correct that. Everybody see this right here? I meant to take the 1.96, but I took the 2.0 because that was the actual velocity. So that was just a boneheaded oopsie by me, but I'm going to fix that right now. And I'm going to write it over top of it so I'll have enough room. So A is equal to negative 1.960 meters per second. Again, we only had two sig figs there, so I couldn't do that. So in this case, instead of an acceleration of negative 2.0, we have an acceleration of negative 1.960 meter. I'm writing it all in red, and it really should be in green. The negative 1.960, oops, meters per second. You can see that 65 times 1.96 gives me 127.4. So I'll get F scale minus 637.0 newtons. And that newton turned it into something that didn't look like an N anymore, so I'm rewriting it. And that's equal to 127.4 newtons. So we see that the F scale, by adding 637.0 newtons to both sides, and it was 637.0, right? Yeah, it was. And that gives me F scale is equal to 764.4 newtons. The ones place nor the tenths place was sig fig, so the F on the scale is 764.4 newtons. The mass of the scale is equal to the force of the scale divided by G. So that's going to be 764.4 newtons divided by 9.80 meters per second. And that gives me, hold on here. I don't know why it's getting a larger quantity. It should be a smaller quantity. We did say the thing was accelerating downward, right? It was accelerating downward. I think you all know that when you take off in an elevator, if you take off upward, for instance, and it's accelerating, you feel your knees give in a little bit because you're actually feeling a little bit heavier because you're accelerating upward. If you accelerate downward, you should feel a little bit lighter. And this is giving me 764 divided by 9.8 gives me 78.0 kilograms, which suggests that she would be showing a higher weight than she's supposed to. And that's not what's supposed to happen here. Let me see. I'm trying to figure out what, if anything, I did wrong. 65 kilograms is your weight times the acceleration. I see. Did everybody see that I multiplied by a negative 1.960, but somehow that number became positive? That's why. Right here, I wrote it correctly, but then I got a positive number here, so that was what went wrong. Let me erase this part since then. So I'm going to erase this, and this should fix it, and this should give us a better value. I apologize for that careless mistake. At least it wasn't a physics mistake. So in this case, we're adding 637 to negative 127.4. So I'm going to say, pay attention to negative sign. So in this case, I'm doing 637 minus 127.4, and that gives me F scale is equal to 509.6 newtons. Again, the ones place and the tenths place were not correct or were not sig figs, so I have to underline them. But the M scale has got to equal the F scale divided by G, because the force of a scale is supposed to be the weight, and weight is gotten by multiplying mass times gravitational acceleration. So if the scale was reading the force, it would read m times g, but since it's reading the mass, it must be reading the force divided by g. That's how I got that. So now I'm going to say 509.6 newtons divided by 9.80 meters per second. Remember, a newton is a kilogram meter per second. So the result should come out in kilograms. So I'm going to take this 509.6 and divide it by 9.8. And that's going to give me what we expected, which is 52.0 kilograms is equal to M scale. Sorry about dropping that sign there. That was tragic. But anyways, we got it right ultimately. Now, for part B, they're saying, what about if the velocity is positive 2 meter or is 2 meters per second downward and there's no acceleration? In that case, watch what happens. So for part B, we have the same diagram: X, Y, 65 kilograms. We still have the F scale pointing up, and we still have the weight pointing down. And that weight pointing down, of course, was 637.0 newtons. And this time the acceleration is equal to 0. So, because of that, the summation of the forces in the y direction equals mass times acceleration in the y direction. And the acceleration is equal to 0. So, in this case, we get F scale minus 637.0 newtons is equal to 0. So F scale is equal to 637.0 newtons. And M scale, which equals F scale divided by G, turns out to be just 65 kilograms for part B. So when the elevator is not accelerating, then the mass read by the scale should be exactly the same as the normal mass. You can do this again with an acceleration in the upward direction, and then you'd see that you'd get like the result I did before. Remember when I forgot that negative, I ended up having basically 127.4 positive added to 637, and that ended up giving me a bigger mass. That's what happens when you accelerate upward. That's going to make your apparent weight a little heavier, and that's why your knees feel a little heavy or a little weak when the elevator first accelerates upward. When it first accelerates downward, you feel your knees are a little lighter. In fact, I used to take my girls on the elevator at my old school, and I would jump really high just before we'd come to a stop, because in that case, the acceleration's in the downward direction, and I was light, and therefore I could almost touch my head to the ceiling, which I'm not that tall of a guy, so it's very rare that I get that high. And then additionally, you could do it on the way down, and you get a bigger weight. So, anyways, hopefully that's something in everyday life that you can compare to what we're doing now in physics problems. Anybody have any questions on any of this? Okay, let's look at example 4.9. I will 4.9 and 4.11. I might have enough time to do that. Let's do 4.9. I'm going to leave 4.10. That's a conceptual one, but 4.9 I think I do have time for. Example 4.9. Adding force vectors. So remember, we learned in chapter 3 how to add vectors. That's never going away. You're going to have to do that till the last day of this class, even if you take the 3 semester portion of the course. And then when you get out of this class, if you take more engineering courses, you're probably going to continue to add vectors there too. So that stuff's not going away. It says adding force vectors. Calculate the sum of the two forces exerted on the boat by workers A and B. That's the whole problem. Okay. So if you look at it, basically what they have here is a boat that we can represent like this. Okay. And then at an angle of 45 degrees, we have a force acting at 45 degrees, and that force, F sub A, has a magnitude of 40.0 newtons. Now, in addition to that, we have a 37.0 degree angle at which another force is acting, and that's going to be force B. And that force B is equal to 30.0 newtons, like that. And what they want to know is the sum of the two forces. So they want to know the summation of the forces is equal to not zero, but question mark. So that's the real problem that they're asking here. Okay. So I'm going to draw a free body diagram like this. There's my X. There's my Y. Here's the mass of the boat. Don't really know it, don't need it because we're just asked for the force. But I do know, for instance, that there is a force, and I'm not going to draw this force green or red because it's not been broken up into components parallel or perpendicular to the X or Y axes. So I'm just going to draw it as blue. And this one has a magnitude of 40.0 newtons. And of course, it's at 45.0 degrees. And then this other one is also not rendered parallel or perpendicular to any axes. So I'm not going to draw it green or red either, but it's 30.0 newtons and it's at 37.0 degrees. So what I can see is that if I try to traverse from the mass M to the end of FA, by going along the x-axis and the y-axis, then I either need to first go along the x-axis to the right, and that's a positive direction. So I'm going to go to the right by a positive direction by this amount till I come up just under the end of that vector. That's the x component of f sub a, is that little green vector there. And I've never drawn a head of a vector so ugly in my life. So that's that. Now, in addition to that, I need to hang a left to get to the head of that vector, and that left direction means I'm going up, so that's also a positive direction. So that's my y component. So this is FA sub y, and this one right here is FA sub x. And we can say that the cosine of 45.0 degrees is equal to adjacent over hypotenuse. Adjacent is the one touching the angle. So that's going to be FA sub x over 40.0 newtons. Therefore, FA sub x is equal to positive 40.0 newtons times the cosine 45.0 degrees. Everything's 3 sig figs, so 40 times cosine 45 gives me 20 times the square root of 2, which is 228.28 newtons in the positive direction. Now, I should actually carry an extra digit, but my calculator is only showing 4 sig figs, so I'm just going to stick with it. Y'all might carry an extra one just to be safe. Oh, actually, no, I am carrying an extra one. I forgot. It gave me 4, not 3. So that's okay. Now I'm going to say the sine of 45.0 degrees is equal to opposite over adjacent. So that means that's FA sub y over 40.0 newtons. And of course, you know that the sine and cosine of 45 are the same. So FA sub y is equal to 40.0 newtons times the sine of 45.0 degrees, which is again 28.28 newtons with one extra digit. Now I can do the same thing for FB. This time, if I want to try to go from the tail of FB to the head of FB, I can first go along the x-axis, and when I do that, I see that it's going to be in the positive direction. So I'll again draw a green vector, and this vector right here is FB sub x. And then I have to hang a right to go downward, and that's a negative direction. So this is FB sub y. So using my trigonometry again, I'll start off with cosine of 37.0 degrees is equal to adjacent over hypotenuse. That is FA sub, or excuse me, FB sub x divided by 30.0 newtons. And remember that the x component is positive, so FB sub x is positive 30.0 newtons times the cosine of 37.0 degrees. So 30 times cosine 37 gives me 23.96 newtons, and that's one extra digit. Similarly, the sine of 37.0 degrees gives me opposite, which would be FB sub y over hypotenuse, which is 30.0 newtons. Now this one has to be negative. I have to force that sign on it. So I write a negative here, and then I write 30.0 newtons times the sine of 37.0 degrees. So 30 times sine 37 gives me 18.05. So this is negative 18.05 newtons. So the resultant x component is FA sub x plus FB sub x plus dot 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 for however many forces you have. And of course, in this case, that means the 28.28 newtons plus 23.96 newtons. 28.28 plus 23.96 gives me 52.24 newtons, and that's in the positive direction. So that's our x component of our resultant. The resultant of our y component of our resultant is FA sub y plus FB sub y plus dot 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 for however many we have. In this case, it was only those two. So in this case, I'm going to say 28.28 newtons plus negative 18.05 newtons. So 28.28 minus 18.05 gives me 10.23 newtons. So we can now figure out what the total vector is. I'm going to draw another coordinate system. It has to be consistent with the previous one or it won't make any sense. So x is positive to the right and y is positive up. And the x component is 52.54 or 52.24. So that's going to be about that much. So that's 52.24 newtons. And then the y component is going to be about 10.23. So, oops. That is also positive. So I'm going to say right here that's 10.23 newtons. And therefore, the final vector for the force is the summation of the forces is equal to R, is that quantity. And this angle right here is theta, and I got to work that out. So R is given by the square root of 10.23 newtons squared plus 52.24 newtons squared. When I do 10.23 squared, I know I only have three sig figs there, and that gives me 104.7. So it's only good to the nearest ones place. And then I do 52.24 squared, and that gives me 272.9, which is also only good to the ones place. So I can add this 272.9. Ooh, excuse me, that's 2,729. Oopsie. Now that means it's only good to the tens place, the tens, not tenths. So that's what we're going to have to add it to. So 22,729 plus 104.7 gives me the square root of 2,870 or 34 newtons squared. Okay. Now remember, we were only good to the tens place, so that means the 4 and the 0 are not sig figs. Now I've got to take the square root of this quantity. So I'm raising it to the zero point 0.5 power, and that gives me 53.23 newtons, which you can see is really, 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 really close to the x component. In fact, it's leaning to being a little bit smaller than the x component, but that's what the magnitude of the vector is. Now, the tangent of theta is equal to 10.23 over 52.24. Oh, I read that earlier as 52.23, not 53.23. It is a little bigger. It can't be smaller than the component. That's what was throwing me. So now the theta is equal to the tangent inverse of 10.23 over 52.24. Again, remembering that those last digits are not significant. So I take the tangent inverse of parentheses 10.23 divided by 52.24, and that gives me 11.08 degrees. So the total force, the summation of the forces F, is the same thing as our resultant vector R, and it is 53.23 newtons at theta equals 11.08 degrees. That's the answer for that one. Anybody have any questions on that? That does seem consistent with what the book has. Uh, we're done with this chapter. You can look up other examples on my YouTube channel. If you have any questions next time, you can ask it. But you guys are free to go. You're always, of course, free to go once the time runs out. And we just ran over by a minute. I'll wait here for the last person to leave in case anybody has any questions. But we have finished chapter 4, and we'll go into chapter 5 next time. Y'all have a good one. Thanks for coming. And I'll wait for the last person to leave before I do.
Have a good one.
Thank you. You too. All right. That looks like it. See ya. Actually, I think I will be solving at least 3 more examples next time from chapter 4. So chapter 4 is not really done. I apologize for saying that. I definitely gonna have to go a little bit further.